Okay, so you saw a very simple example where all we did was add numbers. Now, there are some questions just like this in the homework, and you would expect to see something perhaps like this on the test. The reason that I go through this is that I want you to be sure you understand that this number is negative in all the charts, but you have to change the sign because you're breaking apart that lattice. So you'll see some things like that in the homework and on the Wiley Plus. All right, when you have liquid-liquid solutions forming, it's a little bit different because the molecules of liquid A have to move apart, so this has multiple steps, and that is a potential energy increase, so that's positive. The molecules of B have to move apart, that's positive. Then randomness takes over and wins, and that's negative. So the heat of solution is the sum of all three steps. So when you have solutions forming, depending on the magnitude of these three different energies, it can be positive heat of solution, it can be negative, or it can be close to zero. Now, if the attractive forces of both types of molecules are the same, then the heat of solution is zero. If the molecules are more attracted to themselves than the others, it's going to take energy to break them apart, so it would be positive. And if they are more attracted to each other than they are to themselves, it's going to release energy. So you can have an exothermic solution where delta H is negative and then it feels hot. Or you can have an endothermic where it takes energy to make it run and then it feels cold. When you think of this in everyday life, some examples of this. Have you ever cleaned a plugged up drain, poured sodium hydroxide, Drano, liquid plumber, that kind of stuff in there? And did you ever reach under and feel the pipes? Okay, they get really, really hot. It's very exothermic. And then the most common everyday thing people know of an endothermic solution is you go to the drugstore and you buy those little plastic instant ice pack, they're called, or instant cold packs, and they're a little plastic bag and it feels like liquid sloshing around in there, and then you can feel something lumpy, and when you squeeze it or crack it, it's actually some ammonium nitrate pellets. And when they dissolve, then it gets really cold for a short period of time. It doesn't stay cold. Ice works better, or snow. Snow works great too when you want to pack something, cool it off, right? So those are what you might know from everyday life. Okay, now the last one is the gas-liquid solution. Now the molecules of liquid have to move apart. That takes energy, so that's positive. The gas molecules are already really far apart because gas molecules are far apart. So that one, we don't have to spread apart. So then they move into the spaces and we get randomness, and that's a decrease. So that's a negative number. So again, depending on the magnitude of these two numbers, that can also be positive or negative. And solubility is an equilibrium. So this is the first time that we kind of introduce equilibria to say that we can have this arrow going in both directions. What this means is that you can have material that is dissolved going to undissolved, coming out of solution, and it's going back into solution at the same rate. When we draw the two-headed arrow, it's at the same rate. And we'll talk a lot more about equilibria in the subsequent chapters. But we can have two different situations for solubility. Here we have the dissolved material, and over here we have the undissolved material plus heat. So if I add heat to the undissolved material, I make more dissolved material. This is common. This is what most things are. If you add heat, it dissolves more. This is very unusual, where you have the material dissolved adding heat and you make more undissolved. There are some very rare ionic compounds made with cerium, like cerium sulfate, I think, does this, that when you cool it down, you actually get more dissolving. Most things, when you cool them down, less dissolves, and when you heat them up, more dissolves. So one of the things we start to look at mathematically now is the relationship that pressure has with the solubility of gases. Increasing the pressure for gases that don't react increases the solubility if we increase the pressure at a constant temperature. Okay, so we're holding the temperature constant. So Henry's law is the mathematical relationship between concentration and pressure. Mathematically, Henry's law says C sub G, the concentration of the gas, is equal to K sub H, the Henry's law constant, times P sub G, the pressure of the gas. So when you look at this, remember the numbers we have in chemistry generally have units. So we have to make the units cancel. In most cases, we can have any concentration unit, any pressure unit, and then the K sub H units will be such that they make the units cancel. So you can end up with some really weird units for that. So let's look at an example. Okay, if we know algebraically 2 of the 3 variables, we can solve for the third. Now, I do require that you learn all of these equations. You must know these equations. You will not be provided with an equation sheet on a test. I know some instructors do that in Chem 111, but the reason I do not do that is because I believe that you should train like you test. And as you move forward from here and take your professional school entrance exams and you go into your work, you do not spend your whole day looking on a chart for something. You really have to know this. And on the exams that decide if you get into graduate school or not, they don't give you a chart. So if you start at the beginning learning these equations, you will have a much better outcome at the end, even though you may not like it very well. Okay, let's look at this example.